When broad-spectrum light strikes a physical medium, the interaction is chaotic. Millions of overlapping wavelengths refract, scatter, and absorb simultaneously. To extract precise chemical data from that interaction, we rely on the Beer-Lambert law. But that mathematical relationship demands absolute optical purity, strictly monochromatic radiation, meaning light of a single exact wavelength. Physical laboratory light sources cannot provide this. A tungsten or deuterium lamp emits a continuous continuum of energy. If we pass that raw beam through a sample, the detector receives an overlapping smear of transmitted data, rendering the concentration analysis mathematically useless. To bridge the gap between continuous physical sources and monochromatic mathematical ideals, an instrument relies on a wavelength selector, a mechanical and optical assembly placed between the lamp and the sample to aggressively strip away unwanted radiation. The accuracy of any resulting chemical analysis depends entirely on how effectively this device can isolate a single sliver of the spectrum from the continuum. Selecting that narrow band introduces the core engineering dilemma of spectrophotometry. Isolating a specific wavelength inevitably destroys the light's overall power. This chart displays the output of a typical wavelength selector. We measure its precision using effective bandwidth, the width of the radiation band at exactly half its peak height. A narrow bandwidth is essential. If the band is too wide, it spans multiple absorption peaks, blurring distinct structural details. But precision comes at a cost. Notice the maximum percent transmittance at the top of the curve. Because a selector discards so much source light, the remaining beam is incredibly weak. High transmittance ensures enough photons reach the detector for a stable signal. Every wavelength selector ever engineered forces a strict compromise. Squeeze the bandwidth tighter to gain resolution, and you sacrifice the raw transmittance needed to measure it. To understand how modern instruments navigate this limitation, we have to look at how these optical compromises evolved, starting with the most basic method available. The earliest instruments relied on absorption filters, simple discs of colored glass or gelatin laced with organic dyes. They function through brute force selective absorption. As the full spectrum enters the filter, the material traps the unwanted radiation, converting those specific frequencies into thermal energy while allowing the desired color to pass through. This graph plots transmittance characteristics. Look at the wide curve labeled absorption filter. Its effective bandwidth is massive, spanning 50 nanometers, isolating a large spectrum chunk. Furthermore, checking the y-axis reveals peak transmittance rarely exceeds 20%. The vast majority of light is lost. Because they are optically blunt and consume enormous amounts of radiant energy, absorption filters fail the requirements of precise quantitative analysis. The solution to the absorption problem required abandoning chemical dyes in favor of physical optics. The result is the interference filter. This diagram details an interference filter, a transparent dielectric spacer sandwiched between metallic films. Light passes into the dielectric, reflecting back and forth. As the equation shows, wavelengths matching the thickness undergo constructive interference, reinforcing each other. All others are destroyed. This method yields an effective bandwidth as tight as 10 nanometers, while pushing peak transmittance well above 50%. By turning the wave nature of light against itself, interference filters solve the intensity trade-off. However, their physical thickness is permanently fixed. They provide an excellent beam, but only for a single unchangeable wavelength. To continuously scan across a full spectrum, researchers require an instrument that can dynamically change its output, a dispersing monochromator. Early monochromators used prisms. They operate via refraction, where a material's refractive index varies by wavelength, causing shorter, higher energy light to bend at sharper angles. Standard glass absorbs ultraviolet light, so UV instruments require prisms cut from crystalline quartz. However, crystalline quartz naturally polarizes light, creating double refraction errors. This illustration outlines two fixes. The Cornu prism cements right and left-handed quartz together, canceling polarization as light passes through. The Litro design optimizes this using a 30-degree prism with an aluminized back face. Light reflects back, achieving identical dispersion in half the space. Despite these clever mounts, all prisms suffer from a severe physical flaw. This scale maps the dispersion of both glass and quartz. Notice the crowding on the right side. Prisms exhibit nonlinear dispersion. They separate short wavelengths widely, but clump longer wavelengths tightly together. Because the physical spread of the colors changes continuously across the spectrum, the instrument's mechanical exit slit must continuously widen and narrow during a scan just to maintain a constant effective bandwidth. While prisms made continuous scanning possible, their mechanical complexity and nonlinear output demanded a radically different approach. That approach arrived with the replica diffraction grating, which now serves as the standard dispersing element in nearly all commercial spectrophotometers. A grating is an optically flat surface, a layer of resin coated in highly reflective aluminum, carved with up to 30,000 strictly parallel, identical grooves per inch. This schematic breaks down the grating's mechanics. When incident light strikes this jagged surface, every microscopic groove acts as a distinct scattering center. The diffracted rays overlap, and constructive interference separates colors based strictly on the light's angle and the physical spacing of the grooves. This provides one massive advantage: linear dispersion. The physical distance between 400 and 410 nanometers is exactly the same as the distance between 700 and 710 nanometers. Because of this, the mechanical exit slit can remain at a fixed width for the entire scan. The physics of diffraction do present one major complication. Gratings produce multiple overlapping orders of spectra. A first-order 800 nanometer red wave will diffract at the exact same angle as a second-order 400 nanometer violet wave, perfectly overlapping as they travel toward the detector. Fortunately, the fix is entirely passive. A cheap, standard glass absorption filter placed in front of the slit easily absorbs the higher-order stray light before it ever hits the grating. The diffraction grating dominates optical design because it delivers consistent linear resolution across the spectrum, and the cost of its single physical flaw is simply adding a basic piece of colored glass to the assembly. Filters, slits, and gratings do not function in isolation. They extract precise data only when properly aligned inside a complete monochromator system. In this Cherney-Turner monochromator, light enters a slit and strikes a concave mirror, forming a parallel beam. A grating splits this radiation into angular paths, bouncing them off a final mirror to align one specific wavelength with the exit slit. To scan a chemical sample across multiple wavelengths, the system simply rotates the grating on a precise motorized axis, sweeping the linearly dispersed colors across the stationary exit slit one by one. The modern spectrophotometer operates as a masterclass in physical compromise. By balancing the blocking power of absorption filters, the precision of reflective geometry, and the linear interference of etched gratings, analysts extract absolute mathematical certainty from a chaotic continuum of light.